All right, let's go ahead and work through these practice problems here, starting with a few basic circuits questions. So we have a 50 ohm light bulb connected to a 220 volt outlet. We first want to know the current running through that circuit. So we're going to go to Ohm's law, V equals IR. So 220 is going to be equal to our current here times 50. And we find that our current running through the circuit is going to be 4.4 amps. Moving on to the next question, question B here. We want to know what is the power of the circuit, and so for that we're going to use our power equation, which is just that power is voltage times current. So our power is going to be our voltage, which was 220, times the current that we just found, which is 4.4, and so we get a power here of 968 watts. And then we finish with how much charge flows through the circuit in 1 minute. And for that, we're going to use the equation that really is just the definition of current, and that is that current is the amount of charge over the time. We found that our current was 4.4 amps, so that's going to equal the amount of charge over our time, 1 minute, but we want to put that in seconds, so we're going to say 60 seconds. From there, I would go ahead and cross multiply, and we find that the amount of charge here is going to be equal to 264 coulombs. All right, moving on to our next problem here. We have a 15 ohm resistor connected to a 9 volt battery. We first want to find the power of the circuit. So to do that, we're going to say power is voltage times current. But the problem is going to be we don't yet know what our current is. So separately, we're going to have to use Ohm's law to solve for the current. So V equals IR. That 9 volts is equal to our current times our resistance of 15 ohms. And so we get that our current here is going to be 0.6 amps. We can then use that current in our power equation, and we end up finding that the power of this circuit is 5.4 watts. We then can move on to our second part, where we want to know how long it will take to use 1,000 joules of energy. So this actually goes back to our definition of power, which is that power is work over time, or we can alternatively say power is the change in energy, or energy used over time. So we know our power is this 5.4 watts. We want to know how long it will take to use 1,000 joules of energy. And so we're solving for our time there. From here, I would cross multiply. And so what we end up getting here is 5.4 T equals 1,000. When we solve for time here, we end up getting a time of 185 seconds. That's how long it will take to use 1,000 joules of energy at this rate of power usage. Moving on to our next problem here, we have an 18 ohm light bulb, a 13 ohm toaster, and a 9 ohm radio all connected to a 60 volt generator. So I'm going to start here by just doing a quick sketch of this circuit. So here's my 60 volt generator. I have the 18 ohm light bulb, the 13 ohm toaster, and of course the 9 ohm radio here. And the first question is we want to know what is the total resistance of the circuit. Whenever things are connected in parallel or in series, I just have to add up each individual resistance to get the total resistance of this circuit. And so when I do that, I end up finding that my total resistance here is going to be 40 ohms. From there, I can go ahead and find the total current, which is really the current that's leaving the generator there. And I'm going to do that by doing Ohm's law. So I'm going to say V equals IR. I know my voltage is 60. And the total resistance of the circuit is 40 ohms. And so I get a current here of 1.5 amps. So that is the current that actually leaves this generator here to travel through the circuit. The next question is how much total power is used by the circuit. And for that, I can just do my power equation. I know the overall voltage and the overall current, so my power would just be 60 times the current, which is 1.5. So overall, it's a power of 90 watts. And lastly, I want to know what the voltage is across each individual appliance. And so to do that, I'm going to consider the fact that this 1.5 amps is going to flow through each of these appliances, each resistor, or just treat them as resistors, because they're all connected in series. And when things are connected in series, they all get the same current. So taking that one at a time, we'll start with the light bulb. All right, we know the current going through it is going to be that 1.5 amps. We can use Ohm's law then to get the voltage. So we'll say 1.5 amps times our resistance, which is 18 ohms. And so we end up getting a voltage here of 27 volts. We can then move on to our next appliance, which is the toaster. And so for the toaster, same thing, we're using Ohm's law. Our voltage is just going to be 1.5, which is our current, times our resistance, which is 13 ohms. And so we end up getting a voltage there of 19.5 volts through the toaster. And lastly, we will do the radio. Put that over here. Ohm's law once again. The 1.5 amps of current times 9 ohms of resistance, and that gives us 13.5 volts. And if we wanted to real quick double check, we would see that if we add up those voltages, 27 plus 19.5 plus 13.5, we end up getting an overall voltage of 60 volts, which makes sense because every loop must add up to the voltage of the battery or the power source in this case. Alright, so for this next problem, we now have a circuit connected in parallel. So we have a 120 volt outlet, and along with that we have a 120 ohm air conditioner and a 24 ohm fan. Doesn't really matter what exactly they are. The key is they are two resistors within the circuit. So the first thing we want to do is we want to find the total resistance of the circuit. So for that, we're going to do our 1 over RT equation. That's how we determine the total resistance for objects connected in parallel. So 1 over RT is going to be equal to 1 over 120 plus 1 over 124th. And so we end up with 1 over RT is equal to 0.05. That's when we're going to use that flipper button that we've talked about before, raising both sides to the negative first power. And what that does is it allows us to solve for RT, and we find that our total resistance here is going to be equal to 20 ohms. From there, we can find the total current going through the circuit using Ohm's law. So we can say V equals IR. So 120 is equal to our current times our resistance, which we just found was 20 ohms. And so we end up getting a current here of 6 amps. All right. Moving on to the next question, it says, what is the voltage across each appliance? And so what we have to consider is that each appliance is on its own separate loop. Okay, that's what happens when things are connected in parallel, which means that each appliance is going to get that full voltage of the outlet here, which in this case is 120 volts, because there are two basically independent circuits. There's two parallel loops or two pathways, and each pathway needs to add up to the voltage of the battery. Lastly, we want to know what is the voltage on each one. So we'll start with the air conditioner here, and we'll say that we're going to use Ohm's law, V equals IR. We know it gets 120 volts, and the resistance of it is 120 ohms, which means that our current through the air conditioner is just 1 amp. We can then move on and also find it for the fan using the same basic idea here. V equals IR, so 120 volts equals our current times our resistance, and that allows us to find that the current is 5 amps through the fan. So for this next one, we want to use our voltage and current rules to analyze these two circuits. I'm going to start with the current one, and then we'll move on to the voltage one. So our big idea we remember with current is that current splits at junctions, and the current going into a junction must equal the current leaving the junction. So I'm going to be thinking about my current going up and around my circuit like this, and I get to my first junction right here. I have 7.6 amps going into this junction. 4.7 of it goes straight. The remaining current must go down through here. So I'm going to say 7.6 minus 4.7 gives me 2.9 amps. And that's going to be the current that runs through resistor A and continues on here through resistor B. I then find my next junction, which is right here. I see that I have the 4.7 coming in. 2 amps is going to go down when we want to know how much goes straight. So I'm going to say 4.7 minus 2 gives me 2.7 amps. So that current is going to run through resistor D here, continue on through resistor E, all right, coming all the way around, and then eventually those two currents, this 2.7 amps and the 2 amps that was running down through this branch, come back together at that junction there. And so they're going to combine 2.7 plus 2 to give me 4.7 amps, which runs through resistor C. That eventually does, and we don't have any more to fill in, but that would combine, that 4.7 would combine with the 2.9 to make 7.6 running back around here through our circuit. All right, we're going to move on to our voltage here, and for that, with voltage, we're not thinking anymore about junctions, but we're thinking about loops, and we know that each loop must add up to the voltage of the battery, which in this case is 10 volts. So I'm going to think about this first inner loop here in red, and we know that all the voltages across all those resistors must add up to 10, so I have 2.5 and 3 and this blank resistor, and that must equal 10, which means this unknown resistor here, A, must be 4.5 volts. So that's the first loop I'm going to consider. Next loop I'm going to think about is one going all the way around and through this middle pathway here, so something that goes like this. And so for that, we can think about the fact that we have a 2.5, this unknown resistor here, B, a 3, a 0.6, and another 3, and that must add up to 10. So solving for that unknown resistor there, we find that that's going to be 0.9 volts across B. And then we can go ahead and actually fill in C and D. And for that, we could think about our pathways, but basically from here to here, from the spot where this splits right here to when it comes back together, all those pathways must be the same voltage. Okay, and we could again do each individual path. We could do this path and then this path and solve for it, but the quicker way is because they all split and then come back together, it must be identical no matter which path you take. So all of them must be 0.6 volts. We can then do our final pathway going all the way around the outside here, okay, to get resistor E. And so for that, what we have is 2.5 plus 0.9 plus this resistor E, which is what we're trying to find, plus 3 must add up to 10. And so when we do that, we find that the missing one is going to be 3.6 volts here for resistor E. All right, for this last one, we're doing a full circuit analysis here, trying to find 3 things. We're trying to find the total resistance, total current, and then voltage and current through each resistor. So we're going to do what we've done in the past, breaking this circuit down one step at a time here, looking for simple combinations until we reduce it, and then we'll build it back up, finding those voltages and currents across each. All right, so the first simple combination I see here is R1 and R2. Those are connected in parallel, so we're just going to add up those 2 resistors to get a total resistance for 1 and 2 of 18 ohms. R3 and R4 is another simple combination since they're connected in parallel. We're going to do the 1 over thing there for 3 and 4, and so we end up finding when we do that the total resistance of them together will be 2.25 ohms. We're now going to redraw our circuit here, replacing those. So we have our 12-volt battery. That is connected to R12 here, which is 18 ohms, and then R34 here, which is 2.25 ohms, and then we still have R5 down here, which is 2 ohms. We look for our next simple combination here, which is going to be these resistors in parallel. And so when we combine those, we have 1 over RT is 1 over 18 plus 1 over 2.25. And we find that the combination of 1, 2, 3, and 4 is just 2 ohms. We're now going to do one final redraw here, and then we'll be able to get the overall resistance of this circuit. So we still have our 12-volt battery here. It's connected to R1234, which is 2 ohms, and connected to R5, which is also 2 ohms. And so when we go ahead and solve for our overall resistance here, we end up finding that that overall resistance is 2 plus 2, or 4 ohms. So now we can use Ohm's law to find the overall current, and then we're going to work backwards through our circuit and the voltage and current on each one. And so we can say that we have 12 volts is equal to I times 4, so we find that our current here is 3 amps. So that 3 amps is going to leave the battery. It's going to go through this R1234 as well as R5, so each one of them will get 3 amps. And then going back to Ohm's law, which we of course will be coming back to time and time again as we build this back up, we can say this one gets 6 volts, and this one also gets 6 volts. Now R5 was the original resistor there, so I'm going to fill in my chart over here saying it's 3 amps and 6 volts, and then I'm going to take this R1234 and we're going to step it back one. That came from combining those two in parallel, which means that each one of those resistors will get 6 volts. We know that when things are combined in parallel, each one gets that full voltage, and we can use that then to solve for our current here. Okay, so we can say that through R12 we're going to get 0.33 amps of current. That comes from Ohm's law, and that means that R34 we will get 2.67 amps of current. Alright, so now we're going to step things back one more, and so we're going to think about the fact that this R12 really came from 1 and 2 connected in series, and so each one will get that full current of the battery, which is, or that full current, I should say, which is 0.33 amps. So each one gets that current, and then we can use Ohm's law to go ahead and find the voltage across each one. And so for the R1, which is 7 ohms, we do 0.33 times 7, and we get 2.31 volts. And for R2, we're going to do the 0.33 times 11, and that gives us 3.63 volts, okay, which approximately adds up to our full voltage of 6. Due to rounding, it's going to be slightly off, but we can go ahead then and fill in those voltages, 3.63 volts and 2.31 volts, with both of them getting that full current here of 0.33 amps. Lastly, we have R34 came from these guys combined in parallel. Since they're in parallel, they each get that full voltage here, so both R3 and R4 will get 6 volts. We can actually just fill that in right now. And then we can solve for the current using Ohm's law once again. So when we do that, we get that R4, 6 equals I times 3, we'll get 2 amps. And R3 is going to get 0.67 amps. So we can fill in those final few here. And then we've analyzed circuit number 1. All right, let's go ahead and move on to our second circuit. First, looking for those simple combinations. So we see here R5 and R6 we can combine into a single resistor. So 1 over 18 and 1 over 36. And so we find that 5 and 6 combine to be 12 ohms. We also can combine R2 and R3. They're in series, so we're just going to add them up, 18 plus 6. And so we end up getting a total of 24 ohms for that. We're then going to redraw our circuit here. So we have our 8-volt battery. Here is R1, which is 5 ohms. Then we have R23, which is 24 ohms. Then we have R4, which is 28 ohms. And then, of course, R56, which is going to be 12 ohms. And so we look for our next simple combination, which is going to be R4 with R56. Since they are all combined in series, we can just add them up. So 12 and 28 is going to give us a total here of 40 ohms for R456. We'll then redraw one more time, and then we'll be able to combine. So now I go ahead with redrawing my circuit. So we have my 8-volt battery here. So I have R1, which is 5 ohms up top here. I have R23, which is 24 ohms. And now I have this R456, which is 40 ohms. And I want to now find my next simple combination here. So I'm going to take R23 and R456 and combine them. So 1 over RT is going to be 1 over 24 plus 1 over 40. And when I combine those, I end up getting that 2, 3, 4, 5, 6 combines to be 15 ohms here. From there, I can do one final redraw and get the total resistance of my circuit. I know this one's a fairly complex one, but it's good practice. Most likely you won't see one that's this complex on the test. But again, if you can do this one, you're prepped for basically whatever I throw at you on the actual test. And so I'm going to do my final combination here, which is just R1 in series with R2, 3, 4, 5, 6. And so it's just going to be 5 plus 15, giving me a total resistance here for my whole circuit of 20 ohms. So that answers my first question. To answer my next question, I'm going to go ahead and use Ohm's law. So I'll say V equals IR. So we can say 8 equals my current times my resistance. So I get an overall current here of 0.4 amps. So that is what is leaving my battery and running through the circuit. We're now going to start building this back up. Alright, so now we're going to work backwards and get the voltage and current for each one. So this was all connected in series here. So I can say that that 0.4 amps is going to run through both of these resistors. And then I can use Ohm's law, which we of course will come back to repeatedly to get the voltage on each. And so that 0.4 amps means that this one resistor here is going to get 2 volts, and our other resistor here is going to get 6 volts. So that first resistor, R1, that was the original resistor, so I can fill in that current and that voltage here. This one over here, though, was not. It came from combining these two in parallel. Since they were combined in parallel, it means that each one will get that full voltage, and then the current, of course, will split up. And so using Ohm's law, stepping this back to the previous one, I can go ahead and find the current for each one. And so this current for R23 is going to be 0.25 amps, and then the current for R456 is going to be 0.15 amps. Alright, so we're going to go ahead and step this back one more here. We see that this R456 came from combining 4 and 5, 6 in series. Each one of them we can say gets that full current, 0.15 amps. And then we can use Ohm's law to find the voltage on each one. And so we find that on R4, we're going to have 4.2 volts. And then on R56, it's going to be 1.8 volts. So that R4 was an original resistor, so I'm going to fill that one in. 0.15 amps and 4.2 volts. And then we can go ahead and step this back one more. I am just going to fill in here, nothing changed, but for R23 it's still 6 volts and 0.25 amps. So now I'm going to step this back to my original circuit here. And I'm first going to take that R23, and I see that came from connecting 2 and 3 in series. And so because they were in series, each one of them will get that 0.25 amps of current. And I can use Ohm's law then to get the voltage that's going to be on each of them. So I would find that R3 would be 1.5 volts. And then R2 is going to be 4.5 volts. So I can add those over here to my overall chart, 1.5 and 4.5 for 2 and 3. And both of them get 0.25 amps of current here. Alright, and then moving on to my last 2 resistors here. I have R56, came from combining 5 and 6 in parallel. Because they were connected in parallel, each one will get that full voltage, so each one will get 1.8 volts. And then I can use Ohm's law to get the current here for each one. So when I go ahead and solve for this first one, it's going to be 0.1 amps, and for the second one it's going to be 0.05 amps. Again, just going back to Ohm's law each time. So R5 is 0.1 amps and R6 is 0.05 amps. And then the voltage on each one is going to be that 1.8 volts. And there we have it. That second circuit has been analyzed.